So, today we will talk about discretization of a Laplacian operator. Of course, Laplacian operator in 3D can be written as this form. Here we have directional partial derivatives. So along x direction, also along y direction, and finally along g direction. That is the general form in the Cartesian coordinate in 3D space. However, in this lecture, we will just assume that the system is one-dimensional. So along, for example, along y direction and g direction, then we have symmetry. Then where can you find such a kind of approximation? So think about this one. We have very wide structure. This is wide, and this is x-axis and this is y-axis and this is z-axis, and along y direction or along g direction everything is just homogeneous. How can we find such a kind of thing? It can be easily achieved by certain vapor, and we introduce very deep and wide well formation. For example, this. Let's say that this is quite long, like a micrometer or even longer, and this is also micrometer or even longer. Then in this case, actually the position here and the position slightly shifted from the original position and this position, that position. In this case, here, we assume that everything is quite homogeneous because this total size is quite large and we just shifted a little bit, so along this direction it is assumed to be homogeneous. Also, since the depth is so deep, so we assume also homogeneity. If we assume such kind of thing, we can think about the transport only along x direction and y direction and g direction. Their contribution can be just considered as just multiplying the length along y direction and multiplying the length along g direction. That's it, because they are homogeneous. If we have this relatively narrow resistive load, maybe we can find a certain current conduction I. However, if we introduce much wider one having the same physical properties only geometrically, so we have enlarged it by r times y and r times z. They are scaled. Then what is the current flowing through this wider load? This is current for original structure. Then if we just multiply the length scale by a factor of ry and rg, we will assume that the current is just multiplied. So the conductivity is increased by factor of ry times rg, and also the resistivity is scaled by 1 over ry rg. Okay, so Therefore, if we assume such kind of a homogeneous system along y and z direction, then we can safely say the Laplacian operator for this system can be written as just normal second order derivatives. Okay, so this is one thing. And maybe we can think about a different example. Previously, so just before, I just made a example like this, very wide and very wide. So in this case, we can assume the homogeneity. Also, we have different types of system where one-dimensional transport is valid. So this is an example. Let's say that we have a nanowire. So nanowire by what? Nanowire by a certain semiconductor material. For example, let's assume that this is silicon. Yes, and still we will assume that this is y direction and this is z direction, and this direction, transport direction, is assumed to be x. Then of course in this time we don't have homogeneity. For example, this direction and that direction, we have different directionality. Or if you are confused with this perfectly symmetric case, then let's assume like this. We have a cross section like a dumbbell. Yeah. Then we have also, yes, this is the structure. Then this is x direction and also y direction and z direction. In yz direction, we have no homogeneity along y direction and z direction. Then in this case, can you assume the one-dimensional structure or one-dimensional transport? Even in this case, we will decompose our system into two parts. Here we have y, z plane, and we assume that the physical size of yz plane or physical area of yz plane is so narrow, therefore the electrons are fully quantized inside this small yz plane. In this case, we will consider the electrical structure of electrons inside this yz plane. After that, once we understand the electrical structure, then this transport itself is occurring only along x direction. I want to say Laplacian operator is in principle 3D. However, there are many good examples where the Laplacian equation can be safely regarded as one-dimensional case, and so therefore our assumption like a one-dimensional Laplacian is not that much off from the realistic example, although the problem is simple, but that is really practical. Anyway, we will work with this second order differentiation. Then where can you find it? In the previous lecture, lecture 1, we have studied the analytic solution of the infinite potential well problem. The original form itself looks like this. So this is effective mass, and so this is one-dimensional structure. Then psi equal to E psi. This is the original structure of our problem, and by moving this coefficient into here and just saying that k square is given by 2m star E, then we can arrive this form. And this form, the Schrödinger equation, just to manipulate form, can be regarded as an eigenvalue problem. Here we have eigenvector and our interested operator, and it generates eigenvalue. So today we will try to solve this equation. But anyway, we can understand Schrödinger equation itself can be casted into the form of eigenvalue problem, and the operator related to the infinite potential wave problem or Schrödinger equation is just Laplacian operator. So now our question is, what is the eigenvalue and eigenvector of this operator, second order derivative operator over one-dimensional form of the Laplacian operator? Our goal today is its discretization, not studying the analytic solution, but we will try to solve it with computer program. We are now considering x is larger than 0 or greater than equal and smaller or equal to a. So in this case, we wanted to have the knowledge about wave function. For example, let's assume that we have an analytic solution. This is an assumption. This is happen to be, for example, sine kx. Let's assume. Then, if we have arbitrary numbers like just halfway, what is the answer? When you just insert k times halfway, you will get the answer. Then how about 1/3 a? Then of course you can easily get the answer. Of course, between this position equal to halfway and position equal to 1/3 a, we can find many different, actually infinitely large number of points. For example, just taking half of it, then we can have different numbers. However, our analytic solution can provide us any time, for example, what is the value of wave function at this position. Then we can always just insert our coordinate 5a. Then this is the exact solution. Our resolution is infinite. If you give me an answer about the psi at certain position, whatever value you give me, I can answer by just evaluating this sine kx function. But now think about different cases. This is related with the analytic solution. But how about our numerical solution? For example, in this case, let me assume we have introduced such a kind of discretization. For example, let's call it like this: x1 equal to 0. x2 equal a over 6. x3 is 1/3 a, x4 is just half a, x5, this is 2/3 a, x6, and finally x7 equals a. We have introduced 7 points for a range from 0 to a, and their differences is just a over 6. So a over 6, here you can see also a over 6, also a over 6. Everything is uniformly distributed. So starting from 0, just our differences, then we will get the next position, and add once again, then we will get the next position, next position, next position, and ends up the final destination of A. So let's say this kind of discretization is tried, and let's assume that we have made solution on those points by numerical mean. So after solving the problem, now you have the values of your wave function at these points. You can do it, and we will do it. So let's assume that you have 7 real number for these 7 points. Yes, and we will believe that this is enough for our problem. That is a usual way of our numerical analysis. Then my question is, in this example, when we have the values at halfway and values at 1/3 a, actually this is corresponding to what? Corresponding to, this is corresponding to x equal to x4, and this is corresponding to x equal to x3. So if we are interested the position like x3 or x4, these numerical solution can provide us direct access to our interested quantities because we have it. But here we have this number. This number is given by just midpoint between x3 and x4. However, when we have arbitrary x values, which is given by a midpoint of x3 and x4, analytic solution always gives the exact solution. How about numerical solution? If we ask psi at midpoint between x3 and x4, then can our numerical solution give us any hint about the wave function? Actually, this is not available. Not available. In principle, we have no idea about that. So this is actually the limitation of our numerical solution. So before starting our numerical analysis, my caution or warning about it is, please do not believe that this numerical way of solving the partial differential equation or differential equation gives us the exact solution. Always it gives certain approximate solution under the given discretization scheme. So of course we believe, including me, believe that this is close to exact solution. But this is only because we have made a reasonable discretization and insert reasonably large number of points inside the domain. Otherwise, we cannot have the solution. For example, let's say starting from 0 to a lowest eigenmode, eigenvector of our Schrödinger equation infinite potential wave problem just looks like this. This is a sine function. But if we go to higher mode, then it now becomes full sine function. This is just a half period and this is a full period. And if we go further, then third, fourth, then eventually we will get the sorry about that, we will get this kind of a solution. We can find many folded wave function from 0 to a. Yes, let's say that what is the n number? So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Therefore, this is just ninth eigenvector. Okay, now we have a ninth eigenvector of our Schrödinger equation in the infinite potential well. Then, in order to describe this ninth eigenvector, then how many points are required? Of course, we need many points starting from 0 to a. So, otherwise, let's assume that we have introduced just 3 points. Then we will try to sample 1 point, 1 point, and 1 point. So our information after solving this problem now becomes just let's say we have introduced just 3 points to discretize the system, and this is the solution. Then this solution, does it describe the original ninth eigenvector sufficiently well, or we need more points? So of course the answer would be we need more points. How about more points like inserted here and there? Even in this case, we will have So do you think that this is sufficient to describe the ninth eigenvector? Obviously not. We need a lot of more points to reasonably describe our eigenvector. So my main message in this slide is we need sufficiently large number of discretized points in order to describe our solution. And however, let's go to the first eigenvector. Here we have a first eigenvector, and here I have introduced just 5 points once again. Then let's see what happens. Here 1, 2, 3, 4, 5 points. If we introduce these 5 points, how is your opinion about its description, the quality of description? Then if we assume the just linear variation between position, then maybe we will see this kind of shape. Then maybe you can understand, oh, although that is not that perfect, but well, anyhow, it can describe the overall shape of our first eigenvector. So point is, whether this is sufficiently large or sufficiently densely discretized or not, that is really related to your solution. If your solution is smoothly varying over the domain, then you are allowed to introduce small number of points. However, if your solution is fastly varying over the real space, then you have to introduce quite densely discretized point into your system. To many of you, that sounds quite reasonable and obvious, but I'm afraid that nowadays students are so much familiar with this concept. So therefore, sometimes they treat it or consider it as just granted. But please note that we are now just taking the approximation about the real differential equation. So now we will come back to how can we discretize the system. So let's come back to our example with 7 points. In this case, our 7 points are assigned in a uniform way. If we have, for example, n points, here we have n over 7, then the system or the domain was divided by, so spaces or points are separated by amount of n minus 1 a. So let's just insert 7, then it gives us a over 6. If we have n equal to 100, then what will happen? In this case, we will have just a over 99. And when we have 500, then we will have a over 499. So that will be the way of uniformly discretizing the system. So when you have a look at the formulation here, then you can find that your i's position is given by just I minus 1. This is the index multiplied by our delta x. Of course, delta x given by a divided by n minus 1. So we have I minus 1 only because we start from I equal to 1. Usually I'm working in MATLAB, and MATLAB has one based indexing system. So I will use I equal to 1. I start from I equal to 1 condition. That's the reason why I have here I minus 1. If we adopt zero-based indexing system, then obviously we will have xi equal to I times delta x. So of course, when we start from I equal to 0 and ends up to n minus 1. If we assume this kind of uniform spacing, uniform grid, then we can easily proceed like this. Then here we have uniformly separated positions and we can introduce certain sampled value of wave function. Of course, this psi cannot be the exact psi. So exact psi is the value at any time. So psi x is actually a function. However, psi at x1 or psi x2, it is just a number. This is a function taking a real number and generate a real number, and this is a continuous number. However, this one, psi at x1 or psi at x2, in this discretized sense, we just take discretized number such as x1, x2, or xn, and return the real number. So, in rigorous way, we cannot use the same symbol, this one and that one, because it can give us some confusion. However, for simplicity, I will just use the same symbol psi for its discretized form. So whenever it does not give us any confusion, I will make a mixed use of real function psi and its discretization version psi. Okay. So then now come back. In this example, so since we have introduced n equals 7, we have a position starting from x1 and ends up x7, and we have the discretized values or sampled values of a wave function at those points. So let me introduce a certain notation. The wave function, discretized wave function at a certain position x sub I, then I will in a shorthand form like psi I. So this is our convention. So for example, psi 4 in this case, that is representing psi sampled psi values at x equal to x4. This is the convention. Once we accept this convention, then let's collect all available information about this 7 points discretization. At most, we can have psi 1, psi 2, then up to psi 6, psi 7. That is all information we can expect from this 7-point discretization. So we will say only with this 7 real number, we will say we get the full information about the system. That is our assumption. Of course, when n is not 7, when n is 100, 1000, or 1000, 10,000, or 100,000, then maybe it looks beautiful. However, although this number can be increased, however, it is not an infinity. Please note that this is our limitation. Anyway, we will say that only with this finite length, finite vector containing the sampled values of wave function at discretized points, that is enough for our purpose. So that is one thing. So I think that we have around here. But when you have a look at this line, then the wave function can be described with a vector of starting from psi 2 and ends up with psi n minus 1. There are two missing entries. For example, this one, psi 1 and psi 7 is missing in this example. Why they are gone? It is related with this infinite potential wave problem. So up to now, the discussion is quite general. In general sense, we have to introduce really this 7 entry vector. However, if we are specialized to infinite potential wave problem of our interest, then we can say psi 1 equal to 0 and psi n equal to 0. These are boundary conditions. So therefore, just to directly insert these conditions, assumption of psi 1 and psi n are always 0, then we can get just net quantities which should be solved. So like 6. That is the reason why we start from psi 2 and psi n minus 1. So this is a boundary condition. We have x and we have x equal to 0 and x equal to a. In this continuous x-axis, we have introduced discretization. This discretization containing, of course, this x equal 0 and x equal a, and with a constant spacing, we have introduced the certain specific positions, and they are equidistance. Yes, they are all equidistance, and this position, this specific position is called as x1, and this one is xn, x2, and many others. And instead of having any function over this domain, now we say we have values at this point and this point and this point, this point, this point, that point. We say that this is, instead of having any information, any information around those positions, we will neglect. We don't have to understand about these positions. Only numbers at discretized points are enough for our understanding. That is the situation up to now. So let's say that we have certain positions. However, the operator of our interest is not just a local operator taking the local value, but this is related with the differentiation. Differentiation is always take some differences between neighboring points. If you remember, so derivative is defined as limit of delta, that delta goes to 0, and x plus delta minus x naught, defined at x equal to x naught, and f defined at x naught plus delta minus f x naught. That is definition. So simply speaking, the derivative is always related to the difference of the function defined at two neighboring points. If we wanted to calculate the derivative at this point, what is the df over dx, or what is the second derivative, or what is the third derivative, blah blah blah. If we ask ourselves these questions, that is not trivial. There are many ways to express these derivatives, first order, second order, third order, by using certain discretized values. For example, we wanted to express this one as, for example, x2, 2, 1, 4, by using linear combination of these discretized function values. We wanted to express our first derivative. Also, using these values f4, f3, f2, f1, blah blah, means that the value of a function at given the discretized point, and make a sum of them with weighted sum of them. We wanted to express our second derivative. That is our goal. So there are many different schemes, and I will not talk about all of them, just to give you the most important one inside our semester. Okay, so when we talk about the second order derivative, so one-dimensional form of Laplacian equation, and let's say that we are interested with x equal to xi, then here we have xi, and when we consider xi plus 1, that is located in the right side of our in our x-axis. Yes, we have x-axis, and our point is located here. And here we have also here we have also xi minus 1. Of course, we can find more points like xi plus 2 or xi minus 2, but they are not appearing in our scheme. Of course, there are many other schemes actually using the function defined at those points. Then, generally speaking, if we consider such kind of discretization scheme, then error of discretization goes decreased, so reduced. But anyway, we will use just this 3-point discretization scheme. Then let's say we have a function values here, function value here, and another function value here, and function value here. how can we calculate the second order derivative to this case? Simply speaking, we will assume that the first derivative between xi minus 1 and x is given by the ratio of this difference and this difference. You know, this difference, this x-directional difference is just given by delta x, and this one is given as psi I minus psi I minus 1. So the first derivative can be approximated as psi I minus psi I minus 1 divided by delta x. That is the first derivative. However, this is defined at not xi minus 1, not xi. This is defined between them, in between. For example, here we can assume that maybe the first derivative at this position would be close to psi I and psi I minus 1 divided by delta x. So our first derivative is defined at this midpoint. And in this course, we frequently have to consider certain midpoint like xi plus 1, xi, or xi plus xi minus 1 divided by 2. So this is midpoint between xi and xi plus 1. This is midpoint of xi minus 1 and xi. This midpoint is denoted as xi plus just half, and this one is denoted as xi minus half. This is quite intuitive, so I plus 0.5 or I minus 0.5 means that the quantity defined in between. Oh, but you know, actually we have any information about this virtual position, this integer indexed position. Actually we have the function or unknown variables, wave function, all are accessible. However, this half integer one, that is just in our brain, not existing in reality. So please note that. So anyway, we will assume that d psi over dx defined that x equal to xi plus positive half would be given by psi I plus 1 minus psi I divided by delta x. Also, same quantity defined that x equal to xi minus 0.5 equal to psi I minus psi I minus 1 divided by delta x. So, with this assumption, we can take once again the difference of these and that, these two numbers. Then I want to say d phi dx minus d phi over dx divided by delta x. What is it? This is the first order derivative in discretized form, and here we take the once again its derivative. So it can be regarded as second order derivative form. How about this? This one is simply given by the first one is psi I plus 1 minus psi I. This is corresponding to the first one, minus the second one is given by psi I minus psi I minus 1. Of course, here we have a common delta x, so combined with this delta x once again, we will get delta x squared. So let me just arrange them. Then this one gives us delta x squared appear here, and psi I plus 1 comes from this first term, and here we have minus psi I once and minus psi I twice. So we have minus 2 psi I, and finally here we have minus minus, that is corresponding to psi I minus 1. That is regarded as second order derivative of our wave function. So you can understand now, this is the reason why we are assuming that this form is second order derivative. And please note that this is the evaluated form at x sub I. X sub I means that here we have, since we have x sub I, here we have x sub I plus 1, I minus 1. If we are working with x sub k, then what will happen? In this case, we will have psi k plus 1 minus 2 psi k plus psi k minus 1 divided by delta x squared. So if we are working with 79th position, then how does it look like? It would be delta x squared psi at 79 minus 2 times psi 78 plus psi 77. Okay, let's go to the next slide. Then now we understand our operator, second order derivative operators at x sub I can be approximated by delta x squared psi I plus 1 minus 2 psi I plus psi I minus 1. However, this is for certain position xi. For example, let's assume that we have still n equal 7 example. Then we can evaluate the numbers, this number for x2 and x3, x4, and finally x6. We can evaluate this second order derivative at different positions. So therefore, we can collect them all. For example, this one would be the same factor, psi 3 minus psi 2 plus psi 1. You can do it. Also, if we are going here, then we have psi 4 minus 2 times psi 3 plus psi 2. Same pattern is just repeated with different indexes. Index is also just shifted, and when you go to the last one, x6, and here we have numbers, and psi 6, 2 times psi 5 plus psi 4. Oh, I made a mistake. Here we have 6 and 5, and finally here we have 7. Sorry about that. Yes, we can evaluate the second order derivative not only x2 but also x3 or x4, x5, x6. We can collect those information and make a matrix form. You can easily understand this is corresponding to a Laplacian or second order derivative for n equal to 5 case. So let me just ask you some question. Here we have n equal 7 example. Then how does it look like? How does our matrix looks like? My answer is same. Here we have 1 over delta x. However, of course, here delta x is a divided by 6, and here delta x is just given by a divided by 4. Please note that delta x is a function of our n, and just to fill the matrix. So first of all, it is 5 by 5 square matrix, and it has -2, -2, and -2, and -2, and -2 as a diagonal component. And here we have 1, 1, 1, 1, 1, 1, 1, 1. 4 off-diagonal component by amount of 1 and 3, and all other this empty places. These entries are just 0. That is the common way of discretizing our second order derivative operator into the matrix form. Okay, so time is up. However, I will say here you have certain remaining thing, but that is already covered in our previous lectures, so I will just skip it. Please watch the preview lecture, and we will call it as a day, and we have already covered up to this point. So the missing contents should be studied by yourself, and please submit your homework number 2 by this Wednesday. So you have just 2 days ahead, less than 48 hours, and please write a simple code for solving the infinite potential well problem. So in this case, you have the effective mass and calculate it with different number of n. The reason why I ask you this one is to feel the effect of a number, discretization number. When the discretization number is increased, you will get better solution, and you will get longer simulation time. You can use your own preferred language, MATLAB, Python, Fortran, C++, C, whatever. I love to use of different languages than MATLAB, because when you submit MATLAB, so maybe there are many examples written in MATLAB, but anyway, using the MATLAB is okay, and using the other languages are welcome. Okay, I will wrap up this course and see you this Wednesday. Bye.